Present future is what we're going to talk about, or what I'm going to touch on. That's a lot of ground to cover. And yes, too loud. How do I turn it down? You got it? Is that better? Okay. Well, I'm used to teaching in classrooms, old fashioned, right? Without a microphone. Is that better? Test, test, test. All right. So, wise guy, eh? So, it's kind of appropriate that this is almost exactly 3 years after I gave my last talk. Does anyone remember what that talk was about? Admiral Rickover. So I'm going to start with a quote from Admiral Rickover. And I want you to keep in mind, this is from June 5th, 1953, a memo that he wrote that is highly appropriate to what everybody, there's kind of a rebirth of a push towards nuclear power. Right? So I want you to think about that as I read this quote. Important decisions relative to the future development of atomic power must frequently be made by people who do not necessarily have an intimate knowledge of the technical aspects of reactors. These people are nonetheless interested in what a reactor plant will do, how much it will cost, how long it will take to build, and how long and how well it will operate. When they attempt to learn these things, they become aware of confusion existing in the reactor business. There appears to be unresolved conflict on almost every issue that arises. I believe that this confusion stems from failure to distinguish between the academic and the practical. These apparent conflicts can usually be explained only when the various aspects of the issue are resolved into their academic and practical components. To aid in this resolution, it is possible to define, in a general way, those characteristics which distinguish the one from the other. An academic reactor or reactor plant always has the following basic characteristics. It is simple. It is small. It is cheap. It is light. It can be built very quickly. It is very flexible in purpose. Very little development will be required, and it will use off-the-shelf components. The reactor is in the study phase, and it is not being built now. On the other hand, a practical reactor can be distinguished by the following characteristics. It is being built now. It is behind schedule. It requires an immense amount of development on apparently trivial items. It is very expensive. It takes a long time to build because of its engineering development problems. It is large, it is heavy, it is complicated. The tools of the academic designer are a piece of paper and a pencil with an eraser. If a mistake is made, it can always be erased and changed. If the practical reactor designer errs, he wears the mistake around his neck. It cannot be erased. Everyone sees it. The academic reactor designer is a dilettante. He has not had to assume any real responsibility in connection with his projects. He is free to luxuriate in elegant ideas, the practical shortcomings of which can be relegated to the category of mere technical details. The practical reactor designer must live with these same technical details. Although recalcitrant and awkward, they must be solved and cannot be put off until tomorrow. Their solution requires manpower, time, and money. Unfortunately, for those who must make far-reaching decisions without the benefit of an intimate knowledge of reactor technology, and unfortunately for the interested public, it is much easier to get the academic side of an issue than the practical side. For a large part of those involved with the academic reactors have more inclination and time to present their ideas in reports and orally to those who will listen. Since they are innocently unaware of the real but hidden difficulties of their plans, they speak with great facility and confidence. Those involved with practical reactors are humbled by their experiences and speak less and worry more. That is by the man who is probably done more to develop reactors in a practical sense than any other individual human being in all of history. So let me find the remote. There it is. Okay. So I've broken down a basic outline of the topics I'm going to touch on. Uh, the nuclear power past, including some accidents and different types of reactors that we have built and I'm focused on the United States, not worldwide. Okay, so this is focused on the United States. So uses in the United States. I'm also focused on the private industry, not the military. Okay. The number of operating reactors of the different types I'm going to show you uh, that are currently still operating. And then we're going to look at what kind of idea types are being bantered about now. And it turns out most of them are not new. Most of them have been around since about maybe even before I was born. Okay. So the folks that originally did all of this investigation in the 30s, 40s, 50s, sharp people, very sharp people. And then we're going to look a little bit at development status. And before I go further, based on the memory of last time, so I don't go for an hour and a half, I'm going to set a timer so that let's make it 40 minutes. And at that point, regardless of where I am, I'll stop and see if there are questions. So I don't want to. So first off, what the heck's a nuclear reactor? Right? So basically what we're trying to do with a so-called nuclear reactor in the commercial sense is extract energy from the nucleus of an atom, convert it to heat that we can then use to produce electricity in a practical manner. That's basically what those words say. And there are two types of nuclear reactions that we pursued historically and still continue to pursue in this manner. One is fission, which, as it says, is the inducement by exposure of atom or a nucleus to neutrons of energy level, think kinetic energy, speed, that promote the highest probability that that nucleus will split apart, not necessarily into two equal pieces, okay? And that liberates energy. The typical fuels that are used, that's why I said the word fuel, are uranium-235. What's the number mean? That number is the combination of the total number of protons and neutrons in that nucleus. So in a uranium-235 nucleus, you've got 92 protons, and around the shell, of course, to balance it out charge-wise, 92 electrons. And then the balance of that is neutrons. And then plutonium is 94 protons and same number of electrons. This ends up being produced in every practical operating fission reactor in the country. Okay? Just realize that. I know a lot of people might think, oh, plutonium being produced, bombs, all that. It gets produced. It's, in fact, in any fission reactor in the United States that we're going to talk about, roughly by the end of a given fuel cycle, which is typically 18 months, about 30 to 40% of the power being produced is coming from that fuel right there that is produced inside the reactor itself. The other type of nuclear reaction that we're not currently able to make electricity with, but we're trying to investigate is fusion. What is that? Well, that's pushing subatomic, like the nucleus of a type of hydrogen called deuterium and or tritium. And that just has to do with, does it have in the nucleus a proton and a neutron, that would be deuterium, or a proton and two neutrons, that would be tritium, okay? Pushing those together and getting energy out of that. And of course, it begs the question, how is it that both splitting nuclei can give me energy and combining nuclei in a sense can give me energy? That's what the next thing is designed to answer. And this is a plot of what is called the binding energy per nucleon curve. So of course your first question is, what the heck's a nucleon, right? A nucleon, as the name might imply, is a particle that resides in the nucleus, either a proton or a neutron, okay? Binding energy is the amount of energy, think of it this way, we can look at it from two different vantage points. One is, I have a nucleus. How much energy would it take me to pull every one of those neutrons and protons out of the nucleus and separate it into all of its constituent parts? That's binding energy. Or the opposite. When I combine all of those same particles into a nucleus, energy is liberated. And that same amount of energy is what I had to expend to do the first part, where I said I would pull it all apart. That's called binding energy. What is binding energy per nucleon? It's after we figure out what that total binding energy is to put an atom that's liberated when I put a nucleus all together, or how much I have to expend to pull it all apart. You just take that total divided by the total number of nucleons, and that's the binding energy per nucleon. It's an average. What do we have here? This is the mass number of natural occurring stable nuclei and or atoms. This is binding energy per nucleon, what we just talked about. What this shows you is that depending on where I start in fusion, if I start with very light nuclei like deuterium and tritium, and I put them together to get a heavier nucleus, I end up with something that's more tightly bound, a higher binding energy per nucleon, which means that when I put those things together, they liberate energy out. And similarly, when I had to figure out the laser, when I start with a heavy nucleus like, now why is this, there it goes, uranium, okay, way out here, when I break it into smaller components, I get something with, again, a higher binding energy per nucleon, i.e., from this end of the curve, I get a higher binding energy per nucleon out. I get energy liberated. When I start with light nuclei and combine them together, I get a similar type of thing. Now, obviously, you can see that I get a much larger change with fusion over here on a per reaction event than I do with fission. So you can get nuclear energy out of a reaction going either direction. It depends on what you're starting with. And of course, you might be wondering, well, what's the most stable thing according to this, or the highest binding energy per nucleon? Iron. Iron's right there at the peak. Questions on that? Okay. That's getting too detailed. That's for another day. Now, of course, the investigation into this was accelerated during World War II in the efforts to develop the atomic bomb, starting with Chicago Pile 1, which was a demonstration reactor in, of course, the city of Chicago at Argonne National Lab, or sorry, not at Argonne National Lab, but University of Chicago. The purpose of that was to demonstrate the theory behind a chain reaction. In other words, that a neutron, small amount of neutrons that we start with would induce a certain number of fissions. Each one of those fissions would give us more neutrons, somewhere between 2 and 3 neutrons per fission, essentially more than doubling what we started with, and on, and create more and more reactions. That was the purpose of this. And it was comprised of a bunch of graphite blocks with holes drilled in them for fuel, used natural uranium. Okay, so it was not enriched. For neutron absorbing. So you might say, well, how do I control this reaction? they had determined materials like cadmium that will absorb neutrons, right? So how do you control the reaction? By controlling the neutron population. The neutron population is essentially the catalyst of fission reactions happening. And that's the type of reactor we're talking about, or type of nuclear reaction we're looking at right now is a fission-based reactor, and that's all the ones we're looking at for a while now. So cadmium rods used horizontally, going this way, were used to control the rate of fission. And they had some emergency methods. One was a vertically mounted shutdown rod with basically an axeman and a pulley, okay? And someone with a bucket of salt, cadmium salt solution that they could, on a platform up above that they could dump onto the reactor. Okay? Some pretty, in today's perspective, crude devices. That was called the Metallurgical Lab there at Chicago, led by Arthur Compton. You may have heard of that name. He was a Nobel laureate. And again, it was to prove that the chain reaction would actually work. Once they did do that, they determined that they would need more uranium and plutonium production for developing the bombs, and that's resulted in a reactor out in Hanford, Washington, being built for that effort. Now we'll move on to one of the first practical reactors that was developed. This is the experimental breeder reactor number 1, EBR-1. It was initially designated as CP4. Remember, Chicago Pile was CP1. So this would basically be the 4th assembly, fission-based assembly that was developed. And this is actually a cross-cut view of the plant, EBR-1 out in Idaho. Okay. And essentially, it was think of it as 3 coolant loop type of arrangement. And I'm going to play a little animation of it. Hopefully you can see it. This one used a liquid metal coolant. They called it liquid metal. I'm not sure technically if you would call it metal or salt. It was really they called it in the technical documents that I reviewed, they called it a metal, but they call it an alloy of sodium and potassium, which you don't normally think of as metals, okay? But that's what they called it. Or NaK, N-A-K, right? Why did they use NaK? Well, instead of water. Well, for one thing, it was molten at room temperature, okay? It had great heat transfer and properties, great heat absorption properties. It could hold a lot of heat per pound mass, but it had some drawbacks, okay? For one, it would ignite and burn spontaneously when exposed to air, and when exposed to water, it would explode. Okay? So you got to be careful with this stuff, but it had some great other properties, and that's what's in the little box there. So if I punch this, so this is the primary loop, if you will, of the NaK coming from a supply tank up here, up above, down to the reactor core being heated up. That's why the red heats up. And then through a heat exchanger where it's going to give up its heat to another loop of NaK. Okay, so think of a heat exchanger as just typically on one side a bunch of tubes with some kind of fluid flowing on the inside of the tubes, and then outside of those tubes is a different fluid. So right now we're looking at the inside. Comes down to a receiving tank to a pump, and it just pumps it around in a loop. Okay. The heat is being given off to another loop of NaK, which I've colored orange here. Okay. You go over to another heat exchanger, which is a boiler. That's where, as the name implies, we're going to boil water to make steam to make a turbine go roundy round. Okay. And so you see that we're giving heat from the reactor, from NaK flowing through it, to another loop of NaK that is carrying that heat over to another heat exchanger called a steam boiler. Today we often call that a steam generator. Okay? And then the green is that steam being routed up to a turbine. So the steam pushes the turbine blades around. On the other end of the shaft of the turbine is a generator, and that's where the electricity is produced. Think of it as a magnetic field spinning around, cutting through stationary coils, metal coils, that induces voltage and current that we can then hook up to the wires out on the grid. This was not meant for use to produce electricity for a town or anything. However, it did light up 4 light bulbs. Okay? So it was one of the early reactors used to technically produce electricity, but that was not its primary purpose. Okay? It did demonstrate the concept of breeding. What is breeding? Breeding is when you end up producing more fuel than you consume in a reactor. Okay? And it was successful at demonstrating that. It produced more plutonium. Remember, I mentioned that in any uranium reactor in the United States today used by the industry, we produce plutonium. It just happens. It's part of the, as neutrons get absorbed by what's mostly the type of uranium in the fuel is uranium-238. When that absorbs a neutron, it then transitions through a couple of decays called beta minus decay to become plutonium-239, which is a useful fuel. Okay? So most reactors in the United States, we would call that conversion, converting uranium-238 to plutonium-239. If we produce more plutonium-239 than we consume of what's the main fuel we're consuming? Uranium-235. Okay? Undergoes fission at very low neutron energies. If we're producing more plutonium than uranium that we're consuming, we have a breeder. That's all there is to it. It's very straightforward. Okay. And one of the other things they included in here was what's called thorium-232, another what's called isotope of another element. Thorium exists throughout the world in huge amounts. Okay? Thorium is not fissionable directly. However, when thorium-232 absorbs a neutron, thorium has 91 protons in the nucleus. So if it absorbs a neutron, it turns out it undergoes a beta minus decay that converts a neutron to a proton. Omni-domini, now I have 92 protons and I'm now uranium. I'm no longer thorium. And I'm uranium-233, because I absorbed 1 neutron in something that had a total of 232 nucleons. That made it that total 233. Uranium-233 is very fissionable, and it doesn't make a good bomb. Okay, so one of the things today that people are talking about is thorium-based breeders / converters produce a bunch of uranium-233. That is a great thing to pursue. I'm all in favor of it. Okay. So this was actually demonstrated clear back then. Oh, did I put the year? Oh no, that year they had an accident here and melted down part of the core. So 1951, they illuminated 4 light bulbs. They did have a mistake, an oopsie, in 1955 where they melted down part of the core, but they did end up cleaning that up and continued to operate it again. I thought I wrote down how long they operated that. In case you're wondering, the first reactor plant connected to an electric grid in the world, anyone know who built it? USSR. At Obninsk in 1954, it was a 5 megawatt reactor. Now, that's another thing that might throw you. What the heck's a megawatt? Okay, people have hair dryers. Blow it, it'll dry your hair. A good hair dryer is about 1,000 watts of energy. That's 1 kilowatt. Okay, 1,000 of those hair dryers is 1 megawatt. Okay, so 5 megawatts is 5,000 hair dryers worth of energy. Think of it that way. Okay. We're going to move on to the next type of reactor we're going to talk about, which is the pressurized water reactor. Anyone tell me, hopefully somebody can, who developed the pressurized water reactor? What was my talk on 3 years ago? Rickover, Admiral Hyman G. Rickover. He's the one responsible for developing the pressurized water reactor. What's happening there? Middle word water gives you a clue. We're going to use water as both what's called the moderator. That's the material that slows down neutrons to an energy level where they'll be more probable to cause fission to occur. And it's going to also be the coolant for the core. So it's both things, a moderator and a coolant, a slowing down medium and a coolant. Why do we call it pressurized? Because we pressurize it using something called, amazingly, a pressurizer, okay? That's the only place in this reactor coolant system or primary loop where we want boiling or where we want the water to produce steam. It acts like a cushion. All of the rest of the primary system, and typically there will be like 3 or 4 loops as you see here, so this is a simplified diagram, is subcooled, i.e. you're not forming steam bubbles. Okay? And it's just a pumping water through the core, past the pressurizer on one of the loops. There's only one pressurizer in these plants. So you might have 4 loops, only one of them has the pressurizer connected. But through what's called the steam generator, where it gives up its heat to some other water on what we call the secondary side. Okay, these are thousands of tubes, right? That one tube represents that. And then that steam, there's a lot of other stuff here, moisture separators and everything, goes to the turbine, makes the turbine go roundy roundy. The steam that comes out the bottom of the turbine gets condensed and pumped back into the steam generator. So this is a closed loop. This is another closed loop. And the steam that's making the turbine go roundy roundy is turning the rotor of a generator, which puts the electricity out to you and me out here in the city. Questions on a pressurized water reactor? That's the basic concept, okay? The first civilian reactor of this type that was built at Shippingport, Pennsylvania. Can anyone guess who that might have been in charge of having that built? We got it right. Yes, in 1953, President Eisenhower announced the Atoms for Peace initiative, which proposed a reactor solely for civilian purposes. The one in Russia or Soviet Union that I mentioned was not solely for, it was also used to produce bomb material. Okay? This was solely for production of electricity. This was the first in the world to do that. Initial criticality on Shippingport was achieved December 2nd, 1957, about a year before I was born. And went into commercial operation the year I was born, but a few months earlier. Like I said, it was the first nuclear power plant in the world to be used exclusively for electric power generation. Okay. Produced initially around 68 megawatts, right? So 68,000 of those hair dryers. Okay. And then later they did a what's called a power upgrade to 100 megawatts electric. And let's see, operated until 1982. Then we have what's called a boiling water reactor. The first one of those was the experimental boiling water reactor built at Argonne National Lab. I accidentally mentioned them earlier. A little bit south end of Chicago, where Argonne National Lab is located. First criticality of that was in 1956. What's going on here? Like the name implies, with this reactor, we're actually going to boil the water, middle word is water, right, in the core. So why can I do that here but not on the pressurized water reactor? Well, for one thing, the way the geometry and thicknesses and all of that of the fuel are designed to allow that in a boiling water reactor. In a pressurized water reactor, it is not. Okay? So you can design the fuel to accommodate different styles, if you will, of reactor. What do we have going on? So here's the core. You'll notice a pair of recirculation pumps, they're called, here and here, actually attached to the reactor vessel. Why the heck do we have that when ultimately we want to produce some steam. This is the steam coming out of the reactor vessel going to, now we're seeing a more complex set of turbines, a high pressure turbine and 3 low pressure turbines that then exhaust into a condenser. This is circulating water from, say, a lake or the sea that removes the heat, latent heat from that exhaust of the low pressure turbines, so that it's water again that's subcooled that a pump can then pump into the reactor core again and then just keep that cycle going. What are these for? So these are part of the what's called reactivity control of the reactor. Well, what the heck's that? Reactivity, that word, think of it as it's the trait of a material that allows it to either cause neutron population to go up or go down, okay, i.e. the fission rate. So since the water is our both, remember I mentioned moderator and coolant when I talked about the PWR, it's the same thing here. So if I allow vapor bubbles to form, the steam does not as good a job of slowing neutrons down to the energies that uranium likes to cause fission. So that would be a negative reactivity effect. If I allow more bubbling to occur, that tends to cause the reactor power to go down. If I make the bubbles be smaller in the core, it does the opposite. That's what these recirculation pumps are for. By changing the speed of these recirculation pumps on the sides, I can vary the amount of recirc flow, and I can vary the size and pronouncement, if you will, of the steam bubbles that are in the core, and I can make some small reactivity changes. Make reactor power go up or down a little bit, but just by varying the speed with, think of a varostat, okay? At least in the old analog world. You also have, PWRs are weirdos. In a pressurized water reactor, the rods come in the top. In a boiling water reactor, they got to come in through the bottom. Why? Because up here you got boiling going on. So you want more consistency, basically, in the reactivity effect of the rods. Rods do the same thing we talked about with cadmium. But typically, they're either made out of a combination of silver, indium, cadmium, or they're made out of hafnium. Okay, these are just materials that naturally absorb. Questions on a boiling water reactor? What's going on there? So it's steam that's being produced right in the reactor core itself. Pull out some moisture, send it over to the turbine. Again, push the blades, make the shaft go roundy, and on the far end is a rotor of a generator, electrical generator. That go in roundy, produces AC electricity that out to the world. This is a high temperature gas cooled reactor. The first one of those was built in Pennsylvania, Peach Bottom Unit 1. It's no longer operating. It's helium gas cooled, use graphite moderated. Remember, moderator is what a material is used to slow down neutrons to an optimum energy for the type of fuel that we're using. And in this one, I got to look because I don't have direct experience with high temperature gas cooled reactors because only 2 were built in the United States. And pretty much after the 70s, none were operating. But this one was about 80 miles southwest of Pennsylvania. There's still 2 other units. So there's a Peach Bottom Unit 2 and 3. Those are boiling water reactors. This one hasn't operated since, when was it shut down? 1974. Okay. This used a thorium, remember I mentioned thorium before? Uranium mix for fuel. And again, the use of thorium allows you to produce uranium-233, which is another fuel. So this concept, if you've read about the opportunities for things like how do we produce more uranium and fuel, that concept's been around a long time. And the possibility of doing that has been demonstrated long ago. Well, why would I use high temperature gas like helium as a direct coolant in the core, right? Which then goes to this, oh, there's that word again, steam generator. So obviously we're heating up water to produce steam to make a turbine go roundy and turn a generator again. So that concept should now be pretty comfortable for everybody. And after the helium gives up its heat to the water to produce steam, a compressor, like your refrigerator compressor, only this is a little more sophisticated than your refrigerator compressor, right? Pushes that gas back into the core to pick up heat and head back through the same cycle again. And you'll notice that it's like a pipe within a pipe arrangement that we've got here, where the hot pipe is headed out on the interior of the larger diameter pipe, which is on its way back to the core. So I imagine they did that for preheating and for thermal efficiency, because these were very thermally efficient. What was it? Around 35% or better thermal efficiency. What's efficiency? Efficiency is how much do I get out for how much do I put in, right? That's fundamentally what efficiency is. So if I get out of something, about a third of what I had to put into it, I've got 33% efficiency. That's pretty close to what most pressurized water reactors are. Boiling water reactors are a little more efficient because you have one less heat transfer process, right? Because the steam is being produced right in the reactor. And then these guys, the high temperature gas cooled reactors, were even better for thermal efficiency. They have other problems. So how many were built of each and how many are still operating? Pressurized water reactors, and we're talking about in the utility industry, right? For making electricity, that's what we're interested in. We got these calculating centers that are going to chew up all kinds of electricity, plus more electric cars. So we need more electricity. Historically, 99 were built, 65 are still operating today. Boiling water reactors, historically 34 were built, 31 are still operating. High temperature gas cooled reactors, historically 2, none are operating. The other one was out in Colorado. So that's kind of the history of the types of reactors that we've used in the United States and where are we, how many did we build, where are we today? Now we're going to look a little bit at nuclear industry accident history. This is just the private industry. We're not talking about the DOE and the government. They did even worse. Okay? A guy pinned at the top of the containment SL1 accident. There's some crazy stuff. All right. The number of U.S. nuclear industry, i.e. not military or government, deaths due to excessive acute radiation exposure, i.e. someone got exposed to so much radiation it killed them. 1. His name was Robert Peabody. It happened in 1964, not at a nuclear power plant that produces electricity. It was at a fuel reprocessing plant. The location was at the Wood River Junction, Rhode Island fuel processing plant. So at this reprocessing plant, part of the, and I'm not going to go into all the details of the whole process, but part of the job there was to clean out some bottles that were used with, they would use a solvent, right, to clean out some bottles that were used. Think of it, how do I take a solid rod that's made, that's got radioactive stuff in it, and it's uranium that I want back, and plutonium I want, probably going to have to like melt it with some, or react it with some acid. So I'm going to turn it into a fluid that then I can chemically separate all this stuff. And then I got these bottles I got to clean out, right, for the solvent. So one of the parts of the process was to take an 11-liter bottle. What's 11 liters? Well, that's pretty good size, okay? And shake it for 20 minutes, okay, each bottle, and then dump out the solvent. Now they had some bottles there, some of what I didn't put on here, that were from I don't want to call it an accident, but an issue they had. So they had some bottles with fluid in it that were more enriched uranium than just the average bottle that needed to be cleaned. And from what I read on the NRC's website, he grabbed one of those. Okay? So to make the physical job, now he would have been okay if he had not done the next thing, or if the workers had not done this. In order to make the physical job, again, think about shaking a big bottle for 20 minutes, right? You know, even though Dave and you and I go to the gym, I don't do anything for 20 minutes straight. Okay, so to make the job of separating these impurities out easier, one of the technicians recommended hey, up on floor 3, there's a vat with a big paddle and a motor. Let's put it in there. Okay. Now, a supervisor initially said, nah, we're not doing that. The procedure doesn't say to do that, but then he gave in. Oops. So Peabody goes up there. I think he was only 26, 27, something like that, young man. The edge of this vat was about 5 foot high, and he was only like 5'8" or something. So he's, up like this. And as he's pouring the contents in, he saw a blue flash, and the mix erupted, splashed off the ceiling above him, and he knew exactly what happened based on, he at least had some understanding of what that meant, and knew he was a dead man. And he died about 2 days later. So it's amazing sometimes to look back on some of the things that were done years ago without, uh, proper review of what they were proposing. And it's accidents like this, right, that led in the industry to the emphasis on adherence to procedures, the emphasis on safety, as people could die. How many U.S. nuclear industry accidents have occurred? 56. How do we define what an accident is? Okay. So that is defined based on the loss of at least $50,000 in property damage or loss of life to define an accident. That's how we define what a nuclear accident in the industry is. The two most significant ones in the U.S. nuclear industry, in other words, privately owned, Fermi 1 near Detroit was a fast breeder reactor because of flow channel blockage that resulted in a partial fuel melt. 2 of the 105 fuel assemblies were equivalent melted, and that was on October 6th in 1966. It was the last, right at the end of construction of that reactor plant, they decided to add these kind of plate geometries you can think of as I understand it, was just in case we had a core melt to catch, and then they caused the core melt because they came loose. And then 3 Mile Island Unit 2, which was a Babcock. And so we mentioned pressurized water reactors, right? The word vendor you might run across when reading about the nuclear industry. What's that? That's the company that designed and got the design approved, basically, for a reactor type. Who is the big vendor of the boiling water reactors? General Electric. Somebody here earlier mentioned somebody that they knew that worked for GE Nuclear. There were 3 vendors of pressurized water reactors. Westinghouse, which is the plants that I have worked at, were all Westinghouse. Combustion Engineering, and Babcock and Wilcox. 3 Mile Island was a Babcock and Wilcox design. One significant difference about their design was their steam generators, instead of having what we would call an inverted U-tube, okay, for the tubes inside the steam generator, had a straight through tube that went from the top of the steam generator to the bottom. Why would they do that? Because then they get superheated steam out the top, which is better quality steam in terms of thermal efficiency, but when you lose feed flow to your steam generators. That secondary fluid, which is removing the heat from the primary, it boils off really quick. And that was part of what happened at 3 Mile Island. I'm not going to go into the whole I've taught 3 Mile Island and Chernobyl many times. That's too much for us to cover tonight. Questions on big picture on any of those accidents? That I'm sure everybody here is somewhat familiar with both of those, or at least 3 Mile Island. So what are we looking at for the future? Let me get here. We have advanced versions of both the pressurized and boiling water reactors. Okay? So we're going to look at that. And we're going to talk about small modular reactors, or SMRs, micro reactors, little teeny tiny reactor, and fusion reactors. That was a joke when I went little teeny tiny. They're not really that small. Okay? What's an advanced pressurized water reactor? Okay. By advanced, we mean it's incorporated a lot more passive features. So for example, the reactors built in the 70s, the type that I operated or taught, the criteria was you don't need operator action for at least 10 minutes. The first 10 minutes of the accident, plant does its own thing. Yeah, it's 10 minutes. Okay. These, we're looking at 72 hours. Much longer time frame that the plant can do its own thing, be fine, and an operator doesn't need to basically do much of anything. There are things it can do to help it work better in terms of addressing an accident, but it's designed so that any what we call design basis accident will not result in an excess release to the public, even if I just keep my hands off for 72 hours. Incorporates a lot more natural circulation and use of gravity, i.e. the things that exist naturally to reduce the risk of accidents. You say, well, why didn't they do that before? You did. The plants, the PWRs that I operated are designed for natural circulation to occur, okay? But, 40 minutes is already up. Okay, we okay to go for 10 more? All right. So more natural types of things, advanced cooling systems that use more materials that have been developed that are, material science has come a long way. We can build materials one atom at, at a time. Now, didn't have that back then in the 70s. So materials that improve heat transfer and help prevent overheating and enhance fuel designs. They are now designing fuels that simply won't melt. Okay? So it's pretty interesting to go and research that, look at that online. In the United States, there's one of these plants been built. It's a Westinghouse AP 1000. I'm sorry, two. They are down at Vogel site in Georgia. That's it. Okay. In last year, Westinghouse announced plans for 10 more. They're called AP 1000 because they produce 1,000 megawatts of electricity. Okay. So 1 million hair dryers. Advanced boiling water reactors. Again, instead of needing, remember those two external recirculation pumps? They're moving those right inside the reactor vessel. Now, that begs some other questions, but like, how do I get to them if I need to fix them, right? But from an accident standpoint, that's much better. When you have loops like this, more chance of something breaking off and causing a loss of coolant. Okay? So that should reduce the risk. Previously, so all the boiling water reactors in the United States use what's called a hydraulic drive to drive the control rods up from the bottom. And it's a pretty complex thing. Now they're replacing those with electronic control rods. Much finer control. The other ones, the hydraulic ones, had to move like a notch at a time, like this. Now they'll be able to move nice and smooth. Okay, so you can move it very fine. Better core power distribution control. And the typical standard in the whole industry for, you have certain what we call safety functions that have to be performed to protect the core. Well, you don't want just one pump that can do that. You want at least two, right? Figuring I've got, if one fails, this guy can do the job. If Fred fails, Eric can do the job. Well, now they've said we want Sam too. So now we're going to have three trains of everything, right? That can do the safety function of anything that needs to be done. So that's a new design requirement. There are four of these in Japan, and obviously demonstrated they needed the better ones after Fukushima. We don't have any operating in the United States. What the heck is a small modular reactor? All right, anybody got a modular house that they built? Prefab. That's basically the idea. It's the same idea. It's designed to have a smaller energy output, small physical footprint in comparison to the big, like the ones I worked at put out 1,300 megawatts of electricity. These put out about 300 megawatts of electricity. Okay. And in the world, there are three operating, one in Russia, one in China, one in Japan. Uh, as far as thermal efficiency, I'm not sure. I would expect somewhere in the 30s. You know, actually, I would expect better because I think they're mostly looking at using liquid metal, which again is a good heat transfer uh, medium to use. So it should be maybe more up like 34, 35% thermal efficiency. The concept again is modular manufacturing. Someone mentioned, I think it was uh, Jack, or maybe somebody else, but think of it like an assembly line for cars, right? You produce these modules that then you truck out to a site and you connect it all together. There's your house, there's your reactor plant. Okay, can be transported by truck or rail. Should cut down the capital cost, flexible siting, and like you mentioned, potential for improved thermal efficiency and ultimately efficiency of the plant and safety improvement. Okay, and jobs. It's always good to have jobs. What designs are approved? One, NuScale is the company that actually has two designs approved by the NRC, the Nuclear Regulatory Commission. Two different designs, US 600, US 460. One was approved in 2020, one in 2025. What's that mean? That means they can now be referenced in an application to build. They're not building. What's a microreactor? Teeny tiny. A very small reactor, usually less than 50 megawatts. It'd be bigger than this. Why consider them? They can theoretically be produced more quickly, within weeks, transported, deployed. I'm in a book club with my former Navy Nuke Power School classmates. We do it online, virtual. And last night was our most recent meeting. One of the guys mentioned that the Army, I know I said I wouldn't talk about the government, but he said the Army now has one that they've developed. I don't think they technically would be called that. I think that might be what's called a nuclear battery, and that's a different animal. Uh, yeah, there are things that are called nuclear widget, right? And like the nuclear rockets that they refer to back in the early 60s they were developing was not really nuclear powered. They used a nuclear source, nuclear energy source, like a match to light the blast, which was really a chemical again. Of course, when you think about something that small, then, okay, you need a higher enrichment. Right now, the reactors we operate use about what's called 5% enriched uranium-235. The rest is uranium-238. These need like 20%. What's the problem with a higher percent enrichment? You get closer to bomb material, which means terrorists and those people want it more. And I make this reactor small, it'll fit on the flatbed of a truck. Do you see a natural problem here or risk? So I'm a little iffy about this. Might add to the proliferation risk. Uh, right now, there's not the higher enriched uranium out there on the market. Good. Okay. So they got to think about this a while. So you probably, or you may have heard about microreactors, but I don't know if that's really going to happen. Fusion. I'll just quickly touch on this, and later you can go through. I don't know if they can get to the PowerPoint, or if you can just add that the rest of it onto the thing later. But at least two light nuclei must be brought so close to each other that the strong but short distance of the nuclear attractive force. Somebody over here mentioned nuclear weak and strong forces. That's what you're getting into here, okay, with fusion. Overcomes the electrostatic repulsion. Like charges repel. What's in the nucleus? Protons. They're repelling each other. So how the heck can 92 protons be so close together in uranium? Because of the strong nuclear force. Okay. But you got to overcome that repulsion to get them close enough that they then glom onto each other. Requires the achievement of extremely high temperatures and pressures to cause the fusion process. Okay, very close proximity, i.e. density. Okay. The ions being fused. So what's an ion? An ion is take an atom, okay, like hydrogen has one proton, and if we're using deuterium, a proton and one neutron. Neutron has no charge, and one electron. Remove the electron. Now you have an ion, i.e. it's just the nucleus with a charge, basically. And if you have stripped all of the electrons, let's say off of a helium or something like that, and all you have are charged nuclei and a bunch of them, that's called a plasma. And that's considered often the fourth state of matter, is plasma. There's two types of methods being pursued, even to this day, even when I was at Michigan in the late 70s, inertial confinement and magnetic confinement. Inertial confinement, think of it as you got a little bead. And this time I am talking about a little bead like this size, okay, of deuterium contained in a little sphere, and you blast the daylights out of it with lasers, something like that, and what you're trying to, and you get the little bead material to burn off the outside, which causes a compressive wave inward that then compresses the deuterium and tritium, and hopefully you hit it hard enough that it causes fusion. And the magnetic confinement, you're basically, like the name says, using magnetic fields to contain these plasma, the plasma, which is charged material. Fields, electric fields, interact or make charged particles move or can contain them. So it's a magnetic bottle. And then you can collapse that magnetic bottle onto the plasma, and again, try to compress it and make it happen. This is just a diagrammatic of inertial confinement, hitting a little bead with a pulse of radiation, laser, something like that. The outside burns off, creates a pressure wave inward, compresses the inward deuterium and tritium, and hopefully we get fusion out. And then that is a diagram of a tokamak, which was developed by the Soviets back in the late 50s, as I recall. And this is just, it uses a combination of magnetic coils to create magnetic field running. Both, you can see like a circular pattern. They're actually D-shaped, like the letter D, capital D. And then about 6 or 7 other magnets running this way to create kind of a helical toroidal. What's a toroid? Dunkin' Donuts, standard donut with a hole in the middle, that's a toroid. Okay? You're creating a field like that. This is the plasma, the red, and you're confining it. And then the idea is to get it hot enough that then on this outer wall, you heat up. I haven't seen a good explanation of how the heck are we going to get electricity out of this. Okay? And it's a pulsed type of device. When we want electricity, we want it continuously. We don't want it now. It went away. Oh, there's some more. No, it went away. Okay, that's not what we need. All right. let me skip to the end. There's several other devices. One called the ITER. That is an international project being worked on. First full magnetic powering is expected to be in 2036. First use of deuterium tritium is projected to be 2039. And they're guessing around 2050, maybe they'll produce electricity. I will be 92. It's about as far away as they projected back when I was in college, in other words. There's another company called TAE Technologies, which has achieved some improved performance on their attempt at fusion. That will be interesting to follow. So if you want to look up one that actually has had a recent breakthrough, look up TAE Technologies. I'm not going to go into too much now just because that's kind of what it looks like. You can find these, and it uses what's called a neutral beam technology to help enhance the heating of the plasma before they try and make it fuse. Okay, so you can look that up online. What questions do you have? Sure, Bob. Yeah.
What we're going to do with it.
Okay. Yeah.
And you know, I mentioned Yucca Mountain.
Yeah. Spent nuclear, no, nuclear, not nuclear, nuclear fuel. Hate it when people say nuclear. So Yucca Mountain exists. It's a government facility. Every nuclear plant in the country pays about $1 million a year to the government because the government has agreed they are responsible for the long-term storage of the fuel, and they haven't yet come up with where they're going to put it. So right now, most nuclear fuel that has been used is in what are called dry casks. And these are fabricated on site at all the nuclear plants. They're concrete with proper venting and cooling, air cooled. Remember how we talked about the advanced pressurized water reactors and boiling water reactors using natural circulation, even of air for the cooling? That's what they do. It's not that the fuel itself is open to the air, but there are liners and everything between the fuel that conduct the heat well. For now, that's what's going on. A bunch of spent fuel in dry cask storage out on concrete pads. Eventually, they should be shipped to somewhere like Yucca Mountain. Is Yucca Mountain safe to do that? I would say absolutely. I did research my senior year on high-level radioactive waste storage. At the time, under John S. King, who I mentioned in my previous presentation 3 years ago, and after I got done with that research, he told me to my face, I consider you now one of the top experts on that in the United States, which is quite a compliment to a senior in college that I'd done a lot of work on. Yeah, it's certainly feasible. It's not a technical issue, it's a political issue.
Either Sweden or Norway has used salt beneath the sea and is actually storing spent radioactivity in caves that are over there's thousands of feet underwater as a
I'm not familiar with that. So
yeah, it was in the news maybe 6 months ago.
and
But we've made no progress as we talk about using this again.
depends on what you define as progress. Do you mean technological or political progress, right? Both. And so what are we looking for? We're looking for, in all the cases, even the one you mentioned, a geological stable site, a site that has been stable for lots and lots of years. Now, another thing to think about that I haven't mentioned is we could transmutate a lot of this long-lived radioactive waste into shorter-lived radioactive waste. And that was what EBR, remember there was an EBR1? If there's an EBR1, there had to be a sequel, and there was, EBR2. EBR2 was about to do a demonstration project on that when Mr. Gore and Mr. Clinton canceled the project and shut it down. That happened in the 1990s. That was the very next project. Yes. Can, can you, yeah, I couldn't quite hear you.
I'm sorry. I understood that the French use breeder reactors to
Breeder reactors. Yeah, the French do.
and they have 5%. It becomes waste, and another nuclear engineer friend said you could take the waste that they have and put it in a football field.
Yeah. So they're probably, I'm not technically familiar with what the French are doing, other than I know they use breeder reactors, but I would guess that they're using some form of what I'll call mixed neutron flux to, again, transmutate the longer-lived radioactive products into shorter-lived radioactive products. Again, that's what EBR2 was going to do. Well, you're going to need, you're going to have something that you got to store something, but you may not need a huge amount, right? That's true. Yeah, yeah.
Does the enrichment process need to take place in a close physical proximity to the reactor? And then
No,
my second question, it doesn't?
no. When fuel is fabricated, it's off. I'm trying to remember. A friend of mine was the main fuel procurement engineer for the company I worked for, and it was somewhere down south. The Westinghouse had their facility, but they also went and bought fuel from Framatome, which is the French. They produce fuel that they sell on the market, not at Walmart. But uh, so no, the fuel fabrication facilities can be anywhere.
And so, and then my second question is, what's the difficulty for like the IAEA to determine what's going to be used for legitimate fuel sources versus weapons?
Pretty much enrichment. You know, if they can determine that you're producing, like I said, 5% is pretty much the standard for uh, pressurized water reactors, boiling water reactors that we use. I'm not sure what it is for the French, for what they're doing in their breeders. It's probably some combination of thorium and or just uranium-238. I don't know about how their designs are set up, uh, but there are different concepts that you can breed, create a breeder reactor, obviously. Uh, but trying to remember, what was your question again?
Like, how does the
Oh, the IAEA.
determine weapons grade versus?
They have to be allowed access to go in and assess and evaluate I recall the professor I had at Michigan who wrote the best, and to my knowledge, still the standard book on radiation detection. Len Knoll was involved with them for a period of time. So obviously detectors and that allow you to evaluate what isotopes are where, but uh, access, right? You got to have access to inspect.
What was the news with Terror Power that was just last week or something like that, where they had actually gotten a permit to build something new?
That I missed.
Okay,
Sorry.
I had just
Things are moving so fast. There's so many companies. That was another thing that really hit me in the face. I use the term coal shovel in the face for getting your attention, right? Uh, which some of us are old enough to remember. A real coal shovel is pretty heavy, right? And you get hit in the face with one of those, you're going to realize it. But it was kind of like that. It's like, wow, there are lots of companies right now, not just in the United States, but around the world, looking into new method of enrichment. Used to be only what's called diffusion and or centrifuge. There's another one that is being researched that's very interesting, but I don't understand yet precisely what they're doing in terms of how they're accomplishing the enrichment. Okay, so that's new. There are a number of companies in the researching fusion. A number of companies. Obviously, the government got the microreactor that my buddies told me about last night from somewhere. Uh, so there's a lot going on that I didn't know about, and far too much to cover in a less than 1 hour presentation. Any other questions? All right, I hope you like what I had to present.